Hello, everybody, and welcome to the latest of our webinars from Erlang Solutions. Thanks so much for joining. As always, we'll be on Twitter and Facebook and LinkedIn answering your questions and responding live. So if you've got anything to say to us, please reach out at Erlang Solutions on Twitter. We will also be having the question and answer at the end. You can submit your questions via the question box in your webinar app. Today, we're really excited to be joined by Tyr Chen, who is the VP of Engineering at ArcBlock. ArcBlock are a huge believer in the Beam and one of the founding sponsors of the Erlang ecosystem foundations. So today in the webinar, we're going to find out a bit more about why they're such believers in the Beam, how they've come to choose the Beam, and how they're using it. So without further delays, I'm going to hand over to Tyr for his presentation. I hope you all enjoy.
Thank you. My name is Tyr Chen. Today my talk is building decentralized applications using OTP and Beam. Thanks Erlang Solutions for this opportunity for me to share this how we deal with building these blockchain apps with OTP Beam. So a little bit introduction about myself. I have two daughters. I'm an active programmer. I currently have more than 200 repos in GitHub. I build things in different languages and different type of the applications from CLI to systems. I also write a lot of blog posts. Most of them are in Chinese. And I'm also a marathon runner. So my latest marathon is in Portland, just happened a month ago. So today, I'll mainly talk about what is dApps, what are the requirements of the dApps, and how in ArcBlock we conquer those requirements by using OTP and Beam. And last but not least, we will do a little demo on the Forge framework, which is our main product for building the blockchain applications. First of all, before go into the Erlang OTP world, I have more than 10 years of C experience and 4 years of Python. Both of them are good programming languages, but C has very good performance. Python is very expressive. Then my friend recommended me for Erlang, and then I quickly adopted Erlang because I found the whole mindset or the word view of the Erlang is very, very good. So I started Erlang with a little hobby projects to trying out all kinds of those Gen servers, supervision trees to learn about Erlang. Then in 2015, I started to use Elixir and put Elixir in some real-world usage. And in my previous company, we built a massive video streaming business with Erlang OTP. And right now, for the free advertising-based video streaming, that company is almost the #1 of the market. And after joining ArcBlock, I bring the Erlang OTP Elixir stack to the ArcBlock. So right now, the core infrastructure of ArcBlock are powered by Elixir and OTP, and our Forge framework is also powered by Elixir and OTP. So why do we choose OTP or Beam for building the blockchain products or decentralized applications? There are several reasons. The major benefit I see from the OTP Beam are, first of all, the concurrency is by its nature. So every code you write is a small unit of concurrency. So the system provides you all those schedulers to schedule your work. So you can write code in a very efficient way. And distributed Erlang is also a good choice for us because if you think about the blockchain world, the blockchain or the decentralized apps, each node acts as a full computation power. It synchronizes all the data. It compute those data and generate states by itself individually. Right now, most of the blockchain solutions, they only provide the single node solution. And for Erlang, if we use the distributed Erlang wisely, we can make a logical node backed by a cluster of Erlang node, which act as a single node. So that's a very important feature we see in the OTP and Beam, and we have some experimental usage on that for our own node. And for Erlang, the force isolation and auto healing is a very important feature. So for every process, as everyone, I think everyone knows, every process we can let it crash, and the supervision tree will bring it back. So for all those non-mission critical parts, for example, if a client use gRPC to connect to a node, and the API interaction have any bad issue happened, the current connection just we can just crash the current process, and the supervision tree will bring it back, and user can then she send the next request, it can still connect it to the node. So for all those kind of non-mission critical parts, we just let the process crash and expect the supervision tree to handle everything else for us. And it works really well. We don't need to do all kinds of those error handlings by ourselves. And for the consensus part, if you know a little bit about blockchain, so the consensus part of the blockchain is when a new block, or you could treat it as a list of ordered events arrives, your application need to process those events one by one in order. And by definition, if you have the existing states and everyone got the same new events, and you do the same computation, and your updated states would be identical across the entire network. So if in the middle of processing an event, the process crashed, we cannot just bring it back. We can only let the VM crash, because bringing it back may cause the computation of the state incorrect. So for this part, for this only part, we let the VM crash, and for everything else, we use the VM to do the auto healing for us. And we use the code hot loading very extensively because think about a blockchain application, a lot of code is actually delivered through the network. When a code delivered to the network, you need to extract the code from the network stream, and then install the code and run the code, right? For us, we leverage the Beam virtual machine a lot for this kind of functionality. The code flow into the network is just compiled Beam, and once the node receive this code, the code server will load the new code and replacing the old code. Of course, before loading the new code, we will do a lot of sanity check. We will verify if the sender is a trusted sender, if the signature is correct, if the program meet the basic requirement. But under the hood, the technology we use is just the code hot loading provided by the virtual machine itself. There are other good features in the VM. For example, the CLI. We don't need to implement our own console. The Erlang VM or Elixir VM or Elixir itself have an internal built-in CLI terminal for us, so that our users could just leverage it to do some daily operations. Very handy. After we know why do we use the OTP and Beam for building the blockchain applications, let's have a quick recap on what's the requirement for the decentralized applications or the blockchain applications. By its definition, the decentralized means the network itself is a self-organized peer-to-peer network. It may have the organizational trust among the nodes, or without those trust. Every node is an individual node. Each other cannot trust each each node cannot trust other node. That's two types. So that is called permission-based or permissionless, meaning you need the permission to join the network. That implies other nodes trust you since you are in the whitelist. Or the permissionless, meaning everyone can join the network. Then we need to run certain algorithm to make sure the bad node won't behave, cannot do evil things. So in the case of the node cannot trust each other, we need a Byzantine fault tolerance equivalent consensus algorithm for that. If all the nodes could be trusted, we can use Raft or other technology for that. And the next requirement is every node need to run identical applications and get the application update from the network. So for example, in this self-organized peer-to-peer network, say we have 10 nodes, all these 10 nodes should run in the same version applications. And when an upgrade happened, we need to make sure all the nodes upgrade to the same version without breaking the consensus. So this is very important. That's why the code itself, application code itself, is delivered through the network, and that delivery also falls into the consensus algorithm to make sure everyone pick the new application at the same time, and after everyone picked the new application, the new events will be processed by the new application. So the entire network work as a whole, as a single node. And since we need to make sure every node can deduce the current state from an initial state and then applies them from a list of ordered event. So we need to make sure the node can first of all validate the events which given by its peers, and then consume them in the right order. Everyone else do so. And this kind of computation or consumption is happened independently across the network. So as the consensus converged, the final state, everyone should have the same final state. That's the implication of the decentralized application. And once everyone have the same identical result of the state, then they can start to pick up the next set of events and again and again. So the network evolves or goes forward. You can treat the entire such network as a self-contained word itself. It has its own timer. The timer is when do you get a list of events, and you at even every tick you process those events, and everyone ended up with the same state. And the typical and successful decentralized application is actually everyone is using, which is Git. Although I know everybody now use GitHub a lot, and GitHub is a centralized service for serving your Git repos, but by its when it is born, the Git itself is that you have a repo, others, as long as they can connect to you, they can clone your repo, they can do their own modifications, and then wrap those modifications as a commit and push back to you. So those commits in the blockchain world, you can treat them as a block, and each modifications you can treat them as an event or transactions happened in the blockchain. So now we have a list of requirements of decentralized applications. So how do we conquer those requirements? First of all, for the networking and consensus part, our current choice is Tendermint. Tendermint is a third-party consensus algorithms written in Golang. It's not in Erlang, but we don't fear because Beam can help us a lot with managing those external applications. So initially we use Port to manage Tendermint. And later on, we found this ERL EXEC, which is a really good daemon manager. So we wrapped this application with our own OTP application called a daemon manager, and manage all the daemons our node, all the external daemons, all our nodes need to manage. So initially we use this manage Tendermint. Then later on we use this to manage IPFS daemons, and all of them works really well. And when those daemons crashed, we can get the notification, and our Gen servers could take responsibilities according to the status code of that crash. We can bring the application, we can bring the external daemon up again, or depend on the different status code, we crash ourselves or do other stuff. So this is very, very, very handy and solved our problem. So in future, we may encapsulate lib P2P. Lib P2P is peer-to-peer. Is actually a standard for building peer-to-peer applications, and it has a lot of different implementations. We are looking at the Rust implementation of the libp2p library, and we try to embed that with the Rustler and use that with the Beam. Since I mentioned Rustler is a very good bridge between the Erlang world and the Rust world. If for our application, if there are computation intensive requirements, we will probably go with Rust and use Rustler to bridge it into the Beam. So Beam is quite extensible for handling all these cases. We treat Beam as like Kubernetes for our node, but a better Kubernetes. So the networking and consensus is conquered. Next is the data storage. So since we receive a lot of incoming events, and we need to store the computed states, so we need a good way to store all those data. Those data mainly need to manage as those data itself is a key value based data, but we need to manage them as a Merkle tree or a Merkle Patricia tree to maintain the cryptographical proof and to record the history. So initially in the POC stage, we just, since actually any key store could be used for this purpose, we just need to build a Merkle tree layer on top of that. So initially in POC stage, we use Nisia. The good part of the Beam is that when you launch a node, you have a lot of application available for you to use. For example, if you need a Kiwi store, you can just go with the ETS or Nisia. And later on, if you found you need a better solution, you can find the external solution. So that make you do the prototyping very quickly. You don't need to start with, say, Redis or a lot of other external dependency at the beginning. So in the POC stage, we use Nisia, which is good. And then later on in the real production, we switch to use the RocksDB, because the data volume we need to store typically to hundreds of gigabytes or terabytes or even more. We didn't try with like more than 10 terabytes, but under like 100 of gigabytes of data, RocksDB behaves very well, and its performance is very, very stable. So we choose to use RocksDB for our storage. Then we found this Erlang Rocks DB driver is very, very great. It's I think it directly used the C driver and wrap it into Erlang module. so far we use it without any issue, and it supports a lot of functionalities for RocksDB, including the column families, the backup, checkpoint, all those kind of fancy features. And since since I talked about the Erlang cluster before, about how we want to evolve a single node to a cluster of node which behave as a logical node. So in future, we may support Erlang cluster plus a TI-Kiwi cluster for the enterprise usage, which requires a big volume of data stored in the blockchain. TI-Kiwi is a Kiwi store, is a distributed Kiwi store written in Rust, and I think it is Apache project at the moment, which is quite stable. Next thing is, how do we store the code that requires everyone to have the identical code to run during the consensus stage? So first of all, we store all those code that requires consensus. We call them contract code into the blockchain event or transactions itself, and then each node, when they receive this transaction within the wrapped code in it, if you extract it out and then do a hot reload for the code. So our approach is we compile the contract code to the beam and wrap all those compiled beams into a data structure described as protobuf. If you don't have previous knowledge of protobuf, it's a type. You can create different messages as a Euro struct, but the protobuf's compiler will make sure the encoded data could be transferred across the network safely. So you don't need to worry about the ending issue. You don't need to consider host ending, big ending, little ending, all those stuff. And the message itself is upgradable, which means you don't need to run your own TLV to encode your message. You just use protobuf to describe your message, and once you need to add new fields into the message, it's backward compatible. So that's a very quick description of protobuf. So we wrapped all the binaries of the beams inside the contract, compiled for the contract into the protobuf, and send it across the network as a normal event or transaction. And when the nodes receive the event, it validates the code sanity check to make sure everything's correct, and then load the code into the code server. And the Beam's code server will then mark the existing code which is being used as the old, and this one is new. And in the next round of the, say, if you run this code in the Gen server, in its next loop, if you use the new code. So we control this so that if a block contains the events which have the code need to be upgraded, then after this block, everyone will use the new code to process any future events or transactions. Yeah. So, and since this is we use Merkle Patricia tree to preserve the entire history of the things or the events happened in the application. So we are potentially making a node which could do an auto upgrade from the very beginning to the latest stage. For example, if you have 10 nodes which run for a month, and through this 30 days, there are 5 updates on different contracts. Then a new node joined into the network. It starts from the initial state of the application code, and it gradually pulls a list of ordered events one by one, and then when it meets the event which upgrade the code, it will do the hot reload and do the hot reload and do the hot reload until it catch up with the current software. So software itself could do evolve easily with this. So the Beam using Beam in our SR contract have lots of benefits. In future, we may also think about deliver the code with WebAssembly because WebAssembly could be running in a self-contained sandbox, which means everyone can which means it is very hard for a hacker to build evil code into this this contract and then ruin the nodes memory or disk or the environment. But right now we are using the Beam. So for processing the events happened into the network. So as for now, we are using the Tendermint to push the ordered event list to us. So we use a single gen server, which to process those already committed events. Why do we need to use a single gen server? Because we need to make sure the sequential processing of this, since as I said before, we have an initial state. We need to apply the event which is ordered one by one and generate an updated state. So everyone do this work individually. So everyone's supposed to generate the same state. If we use concurrency, it may mess up the order of the event, which will end up the wrong generated state. So the node could have different behavior, and then the consensus is breaking. So this is how we do the committed order list for the event. We use a single gen server, and for this, as I said before, if the computation fails, we will crash the VM. We rely on the supervisor provided by the operating system to bring the entire VM up again, which means, for example, if you use systemd to supervise the Erlang node, then when the VM crash, the systemd will restart the node. And upon restart the VM, we will go back to the last last block or a last set of event, we haven't finished processing and process them one by one. So this could make sure something bad happen during this computation won't generate a bad state. So if we found so far this logic works pretty well, but in future if we find a single gen server to process the events is a little bit too slow, we may use Rust to we may use Rust and Rustler to offload this logic to an external library, because we will still use the gen server, but the computation will happen on the Rust code, because this part is mainly computation intensive. The benefit of the Beam VM is not in this part. The Beam is good for handling a lot of IOs, a lot of concurrent jobs, but for the single-threaded stuff, it's not the best. And for the events which are received from the peer-to-peer interface or gRPC, which means user send us an event, those events are not wrapped in the in a block, or they are not a committed event, then we will just use a pool of gen server to do the sanity check for those events. For example, when an event arrives, we first need to verify its signature is correct. So those kind of jobs will be done in a pool of gen server, so that the performance will be as good as possible. So that's the basic introduction about how we deal with different situations, how we use the different libraries, different features in the OTP Beam. Hopefully it could give you some hints on that. So a quick recap. For us, OTP Beam and its ecosystem provide us a lot of battle-tested applications for us. So we can just organize those applications or Erlang applications into our node, so that we can build our own solution. The sequential computation and parallel computation, they are both pretty easy in the Beam. We can use a single gen server to do the sequential computing and a pool of gen server to do the parallel computing. And the code server could help us with the code upgrade very easily for this decentralized use case. And for the storage, Nisia is good for is a good start, but since it has some limitations, if we want like other application to be easily interact with the storage, RocksDB or other Kiwi store may be better. The Nisia provided by the Erlang, the main problem is that it mostly could only be used in the Erlang world. The performance of the single threaded Beam is not as good. That's by design. Erlang is not for working for those kind of situation, but we can easily using the existing tools to bring the best of the computation part and the best of the I/O part together by the Beam. So everything I just described above is implemented in our Forge framework, and this is a very high-level graph on how the Forge framework works. It contains like more than 50 different Gen servers to support like the gRPC connection from the client for sending event, for managing all those external daemons as I described, and various daemons for managing the storage, the transaction, and other stuff. So develop such complicated system in Beam. My view is that you can easily make things architecturally right. So you separate things as the Erlang applications, right? This is very high level, and each application you put a supervision tree, and for each supervision tree it manage its subtrees and the processes. So this kind of hierarchy is very natural to the code layout which we have. A lot of other languages, the code you written in your repo is a lot different when running it. So you cannot easily know what happened from which part of the software. But for the Erlang and Beam, you're actually running a self-contained operating systems which have a lot of different applications orchestrated by the Beam itself together to provide a full solution. So when we need to add a new feature, probably we will add a set of new supervision tree under a certain application, or even we just add a new application for that specific purpose and interact that with other applications. So this is very extensible and behaves very well. I still have some time. I can do a little bit, a little demo, and then we can do questions. For our so this demo is mainly about our Forge framework, which as I just described, all those stuff is done in the Forge framework. So we have a CLI which is written in the Node.js, and this can give us interaction on how the chain works or the application works. You can see that I have already started a node. Then I can use a command to connect into my Erlang node, which everyone should be familiar with this interface. Now I'm going to create two wallets. You can see then this wallet is get created. We can just check its status. You can see a lot of information, and since this data structure implement the display protocol, I can show it in a better format. You can see my balance is 0. So let me do a checking, which gets some free tokens. Wallet is W1. And then, hey. I got some tokens, and then if you look at here, this is the web interface for the node. You can see I got a transaction which I do a check-in, and then let me create another. And I like to transfer some tokens to W2. I can just use all those are the contract. I'm currently are using some contracts, and for all the Forge API part, those are compiled protobuf stuff. I can just use transfer and to W2 address and value. I'd like to transfer 1 tokens. Okay, then I sign with my wallet. So I got this transaction, and I can get the transaction to see how it executed. It says okay. Then you could see there is a transaction between my address to this address, and let me go deeper into this address, and this address got 1 token, and my address. After checking, I got 25 tokens, and after I transferred it, I just have 24 tokens. There are a bunch of smart contracts supported from the very trade-specific purpose to the you can create asset, you can create certificate, you can manage your node, deploy new protocols, activate, deactivate a protocol. A lot of things is built in to this system, and you can even delegate your signature to other users, just like how a typical enterprise world would happen. A senior manager delegates its signature right, part of its signature right, to a manager, so that, say, any contract below $10,000, you could sign it. This kind of stuff could be handled this. So we are with Beam, with OTP and Beam, we can easily develop all those contracts. And each contract is actually, let me show you a little bit code. It's actually not so hard. You define a protocol, and then you define a pipeline, what kind of work you would like it to do. There are a lot of default pipelines you could reuse, and then you just write your code. You can write it in either Elixir or Erlang. So I think that's it for my demo. Any questions? I think I still have a few more minutes to take questions.
Yeah, absolutely. So yeah, there are some questions coming through, but also if you would like to ask your own, there is the questions box in the webinar field, so I will still be checking these as I ask. The first one was, how many languages did you look at in your research before deciding on Elixir OTP, and how long did that process take?
Oh, yeah, that's a good question. So I like to explore the new languages. Actually, before Erlang and Elixir, I explored, I used C and Python. I explored Ruby, Haskell, and what else? I think Golang a little bit. Yeah. And then I find this elegancy in organizing your whole system in the Erlang world. And I specifically like the Erlang worldview. Everything is a process. Process is isolated, meaning and process between processes, you can only send message and receive message. If you compare Erlang and Golang, Golang is using CSP for the concurrency. Erlang is using the actor model. Although if you just compare the concurrency part, seems the two language have identical capability, and Golang even in most cases it even run much faster than the Erlang code. But if you look at the from a systems perspective, if you are building a large-scale system, the Erlang code or the Elixir code is much easier to reason and much easier to organize and to learn than the Golang code. Yeah. So yeah, I think that's my answer.
Perfect. Another one we have here. Do you have any concerns over different jurisdictions' approaches to the recognition of smart contracts in law, or is that something you guys aren't considering at the moment?
I don't know if I follow the question correctly. Yeah, right now, to write smart contracts in the blockchain world, there are a lot of different approaches. First of all, I think the smart contract, the word of smart contract itself is not a good word. It's actually just a piece of code which synchronized across the network and executed in each node individually upon the consensus. For Ethereum, they have their own languages. For US, they use C++. And now a lot of blockchain applications started to adopt WebAssembly. And we are a little bit special. We just use the native Erlang Elixir code and organize those code as the smart contract. There are both benefits and good parts and bad parts. For example, for our solution is not for the public chains. Public chain means the chain like Ethereum that everyone can run contract in the node. The solution provided by Forge, or the way we treat the decentralized application is that the owner of the application, they build all those contracts, and their users just use those contracts, and those contracts can be evolved within the event happened in the node. So this kind of approach give us a lot of flexibility. For example, we can just directly adopt the Beam, which is quite good for this use case, to be our native language of the smart contract. But for the public chains, they need to consider a lot of security and safety stuff. For example, if a third party, if a user deploys a contract and that contract can only affect the state inside that contract, cannot go out of control of that contract. So mainly you need a sandboxed environment. Right now the Beam doesn't provide that sandboxed environment, which means if you use the operating systems to compare, our smart contract runs in the ring 0 and the Ethereum smart contract runs in the ring 3, which is in the user mode. You can only affect the stuff in the user mode. And probably for the public smart contract, the future is WebAssembly. So we are also trying to bring it in to the Beam world, so that our node can also interact with the user generated smart contract with the WebAssembly.
Thanks for that. I think potentially some of this was covered in your previous answer, but I'm not 100% sure, so I'll ask. Do you currently use proof of work or proof of stake for consensus?
Oh, we are using the Tendermint, which is a proof of stake. You could think it as a proof of state consensus. Actually, we see it a practical Byzantine fault tolerance consensus is more appropriate. Yeah.
Cool.
But it's a proof of stake. Yeah.
Cool.
Go ahead. Yeah.
And we have one more to get through. How have you addressed the issue of interoperability in your blockchain?
Oh, so for our first of all, everyone can use our framework to create their own permission-based blockchain, and as long as you use our framework to build your chain, we provide a set of functionalities. Let me see, it should be in the swap. Yeah, we use this atomic swap technology to do any asset transfer between the chains across our technology. That the basic idea is very simple. You do a lock in your application, and you do another lock in the asset in another application. Then those two locks locked by a single key. So then you expose this key in the network, and the receiver could use the key to open could open one lock, and then since the key is exposed into the network, you can the other end could use the same key to unlock another resource. Then the data is swapped. So this already supported in the Forge framework. For the cross-chain support between Forge and other blockchain, we are currently trying to support the asset transfer between Forge and Ethereum, and that would happen in near future. Yeah.
Perfect. Thank you so much, Tyr. I think I speak for everyone when I say that was super insightful, and it was really great to have a look at the platform you're building and how you've used Erlang to do it. If you are tuning in at the moment, please know we'll send out the recording within the next week. Included in that email send out will be a couple of blog posts that the ArcBlock team have put together with other details about how and why they are using Erlang, and there'll also be a discount code to see one of Tyr's team members speak at CodeBeam in San Francisco next year. So look out for that in your inboxes. Thanks so much for joining us again, and we'll talk to you again soon.
Thank you. Bye-bye.